example number 3. So example number 3 is this, and if we look at the actual example problem, it reads, determine the normal stresses at the top and the bottom of the cross section shown below, subjected to a bending moment of 4 kip feet. All right, now you might be wondering, well, how do we calculate the bending moment? Where does the 4 kip feet come from? Well, that's a good question. The 5-cent answer is that it comes from statics. A better answer is that we'll talk about it in our next module. So this is module number 4 on bending. On module number 5, we'll talk about the design of beams, and that's where we tell you how to figure out what that bending moment is. All right. So if we're going to solve this problem, then the first thing that we need to do is to identify the governing equations. And the first, that's all right. The first one that we'll use is sigma is equal to, and I'll be formal about it, m times y divided by I. So that begs the question: what are our axes? And so I'm going to make this. In this case, I'll call this an x-axis, and I'll call this my y-axis. The x-axis and the y-axis are almost, the y-axis is almost always vertical, but the x-axis and the z-axis are interchanged depending on the preferences of the author or the particulars of that particular problem. So if we have an x and a y-axis like this, then the z-axis in this case would come out of the plane of the page at us. So what we're going to say then is we're going to take this on, and it's going to expand a little bit. This is going to be minus m times y divided by I, where we're looking at the moment of inertia about the x-axis and the moment that's applied about the x-axis as well. Shucks, golly gee whiz darn. Okay, so this is one of the example problems where we calculated the moment of inertia. And if we were to go back and look at that, I think it's moment of inertia example problem number 13. You can find that posted online. I didn't work it, but it's there for you to work. I did 2 other T problems, so I didn't really think, actually 3 other T problems. I didn't think I needed to do this one as well. So we'll take it as a given in this case that I sub x is equal to nice round number that never stops, 33.33 inches to the 4th, and we know that y bar is going to be 4 inches measured from the bottom of the section. So y bar is going to be measured like that. All right, so we want to find the stress at the top and the bottom fiber. So let's say at the top fiber, we know that sigma is equal to my over I. I'll preserve the minus sign right now and be kind of formal about that. The first thing that we need is the moment m, and the moment is given to us as 4 kip feet. And what we're going to do is multiply that by a value of y that's in inches and a value of I that is in inches to the 4th. So I'm going to convert the moment from 4 kip feet. If I multiply that by 12 inches per foot, so 4 times 12, I should be able to do it in my head, but I'm not really that smart. That's 48 kip inches. If you're not sure about that, just ask my wife. She'll tell you I'm not really that smart. Okay, so I'll plug that in down here, minus m, so that's 48 kip inches. And the value of y that we have, if I'm going from here up to the top fiber, let me draw that in red. So that is the value of y for the top. So we have an overall depth of 6 inches minus y bar is 4 inches. So that's equal to a positive 2. So come back down here, that's 2 inches. Then we divide this by the moment of inertia, 33.33 inches to the 4th. And what we end up with is 2.88 kips per square inch, and the negative sign carries through. Now, usually what I'll do is I'll come in, I should have written it down here before. I'll put a subscript on that, sigma sub, so we know we're talking about the top of the beam and not the bottom of the beam. Okay, So if we calculate the stress at the bottom fiber now, so go in here, say sigma bottom looks like that. And this is equal to minus m times y over I. So in this case, m is still 48 kip inches. I'll just write kin. If you're in Kentucky, you'll know what I mean. And then the distance to the bottom fiber is, let's see, illustrate that up here. So that's this distance here. So that's y for the bottom. All right, boot and that distance is 4 inches. We always measure the y dimension from the centroid of the section, from the neutral axis of the section. The neutral axis is the axis in the section where the stress is neither tensive nor compressive, thus it has to be 0. So the distance here is going to be 4 inches, and since it's measured downward from that neutral axis, that means that it's going to be a negative value. It's in the opposite of the positive y direction. Divide by the moment of inertia, 33 inches fourth. And what we end up with then is 5.761 kips per square inch, KSI. And the sign on that is positive. We end up with two negatives that cancel each other out, and it makes it a positive. So we end up with a compressive stress on the top fiber and a tensive stress on the bottom fiber. All right. So this equation works. And if you are strict with your notation like that, you can get it to give you the sign of the stress with compression being negative and tension being positive. So what if we were to expand on this a little bit? And what if I said, what's the stress at the bottom of the top flange? So let me scroll back up. So you have the flange there. What if we wanted to know the stress at this point right here? Bottom of top flange. Well, there's only one flange, but we're an I shape instead of a T shape. So what if we wanted that stress instead? Well, then we could put in any value of y that we want. So BOTF, bottom of top flange. Let somebody who's trying to watch this without the sound figure that out. All right. My microphone is moving all by itself. I don't know why. Spend 5 hours figuring that out. Okay. So same equation. Whoops. So minus m, moment is still 48 kip inches. So kin, we're going to divide by 33.33 inches fourth. But now instead of putting in +2 for the top fiber or -4 for the bottom fiber, what we'll do is we'll put in this value of y, which is 1 inch. So y TOBF. TOTF? BOTF. Yeah, I screwed that up, didn't I? All right, so then here we put in +1 inch, and what we get for our stress is minus 1.440 kips per square inch. All right, questions, anyone? All right, nobody's got any questions. All right, so if we wanted to, then what we could do is this. We could come down here and I could draw a side view of the section. So let's say that that's the top flange, and then 1, 2, 3, 4, 5. Here's the bottom of the web. So there's the surface. Here's a cut line here. So then in this direction, see, I need blue, that's red. There's blue. So this is going to be the y-axis going up. So x, y. And this will be the z-axis coming out of the plane like that. And then the x-axis is here going into the plane. So that's x. So now what we can do is I can plot that stress. So this is sigma in the x direction. And what we end up with is a stress here that was what, 2.88. So I go 1, 2, almost 3. There's 2.88. And so that stress looks like that. The stress here at the bottom of the top flange is 1.44. So it's right there. I'm not using signs. I know that the stress at the neutral axis, oh shucks, I screwed this up. Let me erase this. the z-axis should come out of the neutral axis, which is 4 inches up, and I screwed that up. So this is 4 inches. So that, oops, just going downhill all of a sudden. There we go. So this is the z-axis here, which represents the neutral axis of the section. This is thus the x-axis going into the plane of the page. So at the neutral surface, at the neutral axis, the stress has to be equal to 0. Then at the bottom fiber, we ended up with 5.761. So let me count over. 1, 2, 3, 4, 5.761 is precisely right there. So then, see if I can use a ruler on this tablet. I'm probably going to scratch it up or something. So there is the stresses in tension. Okay. So, whoops. I guess this is really no different than being in a classroom, except now you can hear me when I mutter profanity to myself instead of in the classroom where you can't. So then down here we have a sigma equal to 5.761. So that's what it would look like. The stress is linear from top to bottom. And if I took some time and drew that a bit more carefully, so let me pan out of this, go to this, then that's what that stress distribution would look like above the surface. So if we go back here to this tab, so if I take this stuff up here and plot it in 3 dimensions, then we end up with that. Okay, so it's there's really a volumetric influence to that. It's not just a plane type of a thing. It's a normal stress. The stress acts perpendicular to the section, but it is actually a stress wedge, or we usually call it a stress block, even though it's not really a block. A block presumes that it's rectangular, but all right. So there's a 3-dimensional nature to it. So let's see. I'm going to go up here for a second. Okay. So one thing that we would do with some regularity is we would figure out how much force is carried by the flange in this section. Right. So we have this top flange, and let me undo that. Let me make the flange in blue. So here's the flange area, like that. Okay, how much force is carried by the flange? So the magnitude of the force that's carried by the flange is equal to the volume of this stress block. So we could say that the force carried by the flange is equal to the volume of the stress block. Stress block, stress wedge. So we could figure that out a couple of different ways. Most simply, if we just take the volume of that, we can figure out, let's see, we can say that the volume V is equal to, let's see, we have 5 inches here. We have 1 inch there, so that surely comes in. So 5 inches times 1 inch. And then what we could do is we could take the average of these two stresses here, and that would give us the 3rd dimension. So then we could say that's equal to 2.88 KSI plus 1.44 KSI, oops, divided by 2. And so then what we would end up with is that it would be 10.8 kips. And since that stress is in compression, that would be a compressive force. All right. Now, there's a more elegant way of doing it. I won't try and pretend that it's better, but it is more elegant. We could use calculus to do this instead. So let me zoom out a little bit and scroll down. And what I can do is I can sketch that I could sketch the problem again here. So top flange is 5 inches wide, 2, 3, 4, 5. I need to calibrate my tablet a little bit. That's 1, 2, 3, 4, 5, like that. Okay. Now let me zoom in on that. So if blue is that con, okay, so there's the x-axis again. Here's the y-axis. Now z-axis is coming out of the plane of the page. What I can do is I could take the force is equal to the integral of the stress times dA. And what I can do then is have a differential area dA that looks like this. Trying to draw too small, I think. So that's dA. And so this dimension then is going to be dy. And the horizontal dimension is going to be the width of the flange, 5 inches. And so what I want to do is I want to integrate over the value of y from y equals 1 up here to the value of y equals 2. So let me go back over here. I can say that f is equal to the integral of sigma times dA, and this is going to be sigma times 5 inches times dy. And I'm going to integrate from 1 to 2, and then the next step is to substitute in for sigma. So then I can say that this is equal to the integral from 1 to 2 of sigma is equal to m times y divided by I times 5 dy. So, oops, there we go. Okay, so let me keep working this integral. So f is equal to, see, m and I are constants. I forgot my minus sign. So there's minus m over I comes out of the front. And then I end up with, whoops, 5 comes out as well. Put in parentheses like that. So then I end up with y times dy from 1 to 2. And then I can evaluate that integral minus m times 5 inches divided by I, all times y squared over 2, evaluated from 1 to 2. Okay, just keep working that with the math. Oops, didn't mean to go that far. Then we end up with minus m times 5 inches over I. And we put in 2 squared is 4 divided by 2, minus 1 squared is 1 over 2. And now if we plug in, we end up with minus 48 kip inches divided by 33.33 inches fourth, substituting in, times 5 inches. And then here we end up with 1.5. And it works out that we get minus 10.8 kips. So you can figure out what the force is that's carried by that flange. Okay, strategic pause. All right, let me scroll back up here to the top. Wow, that's big now all of a sudden. Okay, if I were going to look at this, I could continue this sketch and make it a little bit more complete. We have compression on the top fiber, and we would also have tension down here below, like that. And that tension stress would go from a maximum at the bottom fiber down to this point down here at the bottom, like that. So I've drawn it in green to indicate tension, even though that's not necessarily. So this line would be better drawn like that, I suppose. Good thing I don't have a ruler when I'm in the classroom. I'd never get anything done. Damn picky. Shit. I mean, shoot. All right, and then we put in our stress lines like that. All right. So these are all tension stresses. So the what I'm getting at with this, zoom out just a little bit, is this, that there we go. Okay. So in compression, we could represent this stress block up here with a force that acts in compression like that. And we could do the same thing with the tension force down here. So F tension. And those forces act through the centroids of those areas. So with respect to this tension block down here, there's a centroid, and it's a volumetric centroid, not a two-dimensional centroid. And this force that's in tension acts through the centroid of that. So it's just a triangular wedge. Up here at the top, the centroid is a little bit more complicated because we have this little piece that comes down in the web there that adds some complexity to that. But there is a centroid to that, and we could calculate it if we so desired. And that compression force acts through that centroid there. Now, if you look at this, in order for that to be in equilibrium in the z direction, the force that's in tension has to be equal to the force that's in compression. Otherwise, there would be an acceleration and blah, blah, blah. But so there has to be equilibrium there. So there's also a distance between these two forces. So there's some moment arm. We could call it D. We could call it A. Different textbooks call it different things. And it works out that the bending moment is equal to the force in compression times that distance D, or it's also equal to the force in tension times that distance D. And it circles back around to where you can represent the force that's in a flange or in a component or a part of your cross section as a concentrated load equivalent. And then that force times the distance is representative of the moment. All right, let me check something over here. All right, so so what did we do? We used the equation my over I to calculate stress. We recognize the different stresses that we have, the different moments of inertia. If you have a moment that's acting about the z-axis, you need to divide by the moment of inertia with respect to the z-axis. If you have a moment of inertia, if you have a moment about an x-axis, you divide by the moment of inertia about the x-axis. The stress that results is perpendicular to the plane. So if we have a moment in the z direction and y is vertically upward, then the stress is in the x direction. If you have a moment about the x-axis and y is vertically upwards, then you have a stress signus of z instead. And then you can calculate the stress. The distribution of stress over the depth of the part is linear. And